All right, hi everybody. This is worksheet 9 on Snell's law, mirrors and on mirrors and lenses. So we kind of lightly discussed on the previous worksheet what Snell's law is. Here we have it again. Below that, we have equation 2, the mirror and lenses equation. I use DI and DO. I just find those, it's the distance to the image, distance to the object. That's just easier for me to work with. And we know F is the focal length of the lens there. Okay, I gave you a magnification equation. We have 2 different ways to solve for that. And we have an index of refraction equation. Okay. And I included below that, there's a few tables here, and that will kind of tell us information about these variables that make up the mirror and lens equation and the magnification equation for that matter. For example, with a mirror, we can determine if it's concave or convex, if it's plus or minus, the sign's negative or positive. And then same thing, if it's a real image, virtual, converging, diverging, upright, inverted, we get all this information due to the sign. So I find this table was helpful, and it's something I actually just memorized, and it allowed me to quickly work it out. And also, in memorizing the table, it can kind of direct how you're solving these questions. You'll be like, if you're solving like a one lens situation, you would expect the image to be on the other side. So when it's on the other side, it would be positive. So if your number came out negative, you'd be like, in a mental check, you'd be like, oh, I did something wrong. Let me go back and look at this. Something else worth mentioning is they could totally give you, let's use a diverging lens, for example. They could say like the first lens is converging with a focal length of X, and the second lens is a diverging lens with a focal length of Y, et cetera, et cetera. And that Y, I didn't say negative Y, I just said Y. And then they expect you to know that that Y would be a negative, right? Whenever it's like the focal length of a diverging lens is negative. So you have to be very careful when you're reading here. Like if they tell you it's an inverted image, it's going to be negative. So these little words will kind of cue you into the sign, but they won't always give you the sign when they're presenting the number within the question. All right, so we're just going to start off with a fairly simple Snell's law type question here. And I like these questions that they're just, kind of fun to work through. So let's see, we have our 3 layers. Something like this. Okay. This is H2O, which has an index of refraction of 1.3. This is some material X. And this is air at the top. Okay. So they give us that this angle is 65 degrees. And they give us that this angle right here is 45 degrees. So using Snell's law, we're looking for in part A, the index of refraction of that material X. So, we're looking for NX. So say NX sine theta 1 is equal to N of H2O sine 45. Okay. So what's theta 1 now? If we look at our diagram here, is it the 65 degrees? No, it's not. The angle of interest here is always the angle between the ray of light and the perpendicular line that breaks the surface, right? So we have the H2O surface being the straight line within like a, it's like west to east. It's going like a straight line this way. And then we have a vertical line breaking it down the middle. We need to use the angle that connects the ray to that vertical line. So it's not 65, but rather it's 90 minus 65, which is 25, which we're going to call theta 1. Okay, so we have theta 1 now. Now to solve for NX, we just have to rearrange. We'll get NX is equal to 1.33 sine 45 divided by sine 25. NX would be equal to 2.23. And there's no units on these things, just as such. All right. And then in the second part, we're asked to find the angle that light makes when it exits into the air, right? So we're looking for, where is our angle? Between this surface and the line, or between this vertical and the line of light? Between the vertical and the line of light. Remember, it's always the one that's perpendicular. I call it phi right there, phi or phi. And then we have to draw the other angle on the interior here because we need those two angles for Snell's law. And if you have a good eye, you'll see that these are alternate interior angles. So that means this right here is also 45 degrees. Again, touching this perpendicular line that we have, like, going right through the surface. So in part B, we'll say NH2O sine 45 is equal to N air sine phi. We can get that angle on one side and set that equal to the inverse sine 1.33 sine 45 divided by 1. So that's like index of refraction of air. And this angle comes out to be 70.13 degrees. Cool. So I'd say pretty easy one here. The important thing to remember is that, we have our ray of light going like this and up here and whatnot. You use the angle that connects to that perpendicular. And other than that, this one's just a pure plug and chug. Now let's take questions on this one. All right. Question number 2 here, we have an object that's 3 centimeters tall. It's placed 16 centimeters from a converging lens whose focal length is 12 centimeters. And a diverging lens with a focal length of 10 centimeters is placed 36 centimeters behind the converging. So we have the height of the object. We know the distance from object to the lens. We know the distance between the two lenses. We know the first lens is a converging positive 12 centimeters. We know the second one is diverging minus 10 centimeters. Okay. And then in part, and they're both on the same axis. So, they're both as shown in the picture. And then in part A, we're asked, where is the final image formed? So what we're looking for is DI2, where the final image is formed. So let's first start by solving for DI1, because we know, so let's call this part 1 here. We can solve for DI1 because what's known here is DO1 and and 1 over F1, right? You're gonna do some rearranging, and what you're gonna get is DI1 is equal to 1 over F1 minus 1 over DI1. I'm sorry, DO1. So then DI1 is equal to 48 centimeters. Okay. So we know where the image is. It's going to be somewhere over here, right? Because we know X is 36 centimeters. So let's call image 1. I'll just put like an I1 here. I'll label it. I1 is somewhere out there. However, what we're looking to plug in is how far I1 is from the diverging lens. So DO2 serves as DI1 serves as DO2, right? So the image by 1, the first lens, serves as the object for the second lens. However, we can't plug in this 48 centimeters because that's relative to the converging lens's position. We need to do some subtraction to find out how far I1 is from the diverging lens. So to do that, we'll say DO2 is equal to X minus DI1. The order of this is important, right? DO2 comes out to be minus 12 centimeters. And that's because of the way it's ordered, right? We're doing a smaller number minus a bigger number. And this negative actually makes sense because now we're on the opposite side of the diverging lens, which would otherwise report a positive here. Okay, so with DO2 and F2 for that matter, we're able to solve for DI2. So again, kind of a similar process here. 1 over DO2, just solve for, plus 1 over DI2 is equal to 1 over F2. You're going to rearrange this, solve for DI2, which is going to be equal to 1 over minus 10 plus 1 over minus 12. DI2 is equal to minus 60 centimeters. Bam. Okay, that's part 1 down. So in part 2, we're asked to solve for the total magnification. So to solve for total magnification, I like to call that M total, right? we need to consider the magnification of one lens and the other. So I'm just going to say M1 times M2, where M1 is equal to minus DI1 over DO1. And then M2 is equal to minus DI2 over DO2. These negative signs cancel out. Set our equal sign here. Comes out to positive 15. Okay, so it's 15 times enlarged. That's M2 equals 15. Part B done. The next thing we're asked for is to determine the the size of the final image. So we're looking for the height of the final image, H2. So again, we can use this M total value to solve for that because we know the initial height and we're looking for that final height. We're going to do some rearranging. We're going to say HI, that's what we're looking for, is equal to the M total times the height of the object. So we rearrange this equation. HI, this is part 3, right? HI is equal to 45 centimeters. Okay. And that makes sense, right? Like we know the original height is 3 centimeters. We know that the magnification is times 15. So 3 times 15 is equal to 45. That makes sense. Final question. Is the image real or virtual? So because there's a few ways we can show this. First of all, we remember the table. We have an image that's negative that tells you that it's virtual. Also, if you know, like just positionally, it's behind the, if it's in front of the diverging lens, it's also virtual, right? So I personally just memorize the table and know when I see my final image, my DI2 is negative, that tells me it's virtual. And like if you wanted to say like positionally why that is, we have the object of the diverging lens is this image 1, right? So that means it's going to like see the light through, well, it's going to be like somewhere all the way over here. So it's going to be in front of the diverging lens, which also means it's virtual. So again, 2 things told me it's virtual. First, you can just memorize the sign of the final image, or 2, you could know that, this is a lens. So that means the image is going to have to be somewhere on this side. And because it's in front of the diverging lens, it is virtual. Okay. Okay, so number 3 here, we have light traveling through these 4 layers of glass. Each has a different index of refraction, right? And we want to determine the time it takes for the light to go through each of these pieces of glass. And each one has like the same distance from like one side to the other. I call that D. So when we're asked to solve for time, we need to always consider, like for me, that always reminds me to start thinking in terms of velocity, right? Because if we recall, velocity is going to be equal to some distance over a certain amount of time. And per that notion, we know that our index of refraction equation, that's what we have on our first page is n equals c over v, where c is the speed of light. But we can rearrange that equation such that we're solving for v. So we'll say is equal to c over n. And now we can use this expression right here to solve for the total amount of time that it takes to go through each one of these, right? So we'll say P is equal to ND over C. Now this is going to be a critical equation here when we solve for everything, because we'll say, the time it takes, like this is basically saying the time it takes to go through each one of these 4 things. So how is all that set up? It's going to be N1 D over C plus N2 D over C, and I'm just saying dot for N3 D over C and N4 over C. What we can do is factor out D over C, and what we're left with is N1 plus N2 plus N3 plus N4. And that will equal to the total time that it takes to go through each one of these. This equation itself represents the time to go through one. This equation right here represents the time it takes to go through each one of those. Total time comes out to be 3.11 times 10 to the minus 11 seconds. Okay, so yeah, super fast. So time total is equal to that. All right, So this one is just important to demonstrate that we can consider velocity in these equations, especially when we're solving for time. All right, question number 4. I mean, this one is as simple as it gets. Basically here, we have a certain lens that focuses light from an object that is 1.55 meters away, and the image as an image that is 48.3 centimeters on the other side of the lens. So, we have a lens situation, object on one side, image on the other, lens in between, simple as it gets. What type of lens is it? What is the focal length? Is the image real or virtual? So 1 over that focal length is equal to 1 over DO plus 1 over DI. They give you DO and DI, you solve for F. F is equal to 0.368 meters. Okay. So, here they give you something in meters and something in centimeters. Just make sure you convert to one or the other. Also, in these questions, you can solve the entire thing in terms of centimeters because it always cancels out. Most of the time you need to convert to meters, but like with these ones, you can convert to centimeters. But, if they give you a combination of variables, you have to choose one or the other. And now the more important part here is we want to determine what type of lens is it, converging or diverging. Well, I'm going to look at the focal length. I see that it's positive, therefore converging lens. So CON there. And the next thing we're asked is the image real or virtual? Again, we can look at our table that's on the we can look at our table that's on the first page, and we can consider DI, which is positive, and for that matter, DO, which is also positive. So in that case, it's a real image. I like to look at DI though. So DI positive, therefore it's a real image. So I'll say real also. So that's kind of, this whole question is pretty simple, but it's to show you that just know that table, understand that the object's on one side, lens in the middle, image on the other, it's a real image. Okay, this one's pretty quick, so we can just jump into number 5 here. All right, number 5. And here we have a dentist wants a small mirror that when it is 2 centimeters away from the tooth, it will produce an image that is 4 times an upright image. What kind of mirror must be used, and what must its radius of curvature be? Oh, I forgot to give you the radius of curvature equation, but that's R is equal to 2F. Okay, so that's basically, the focal length, and then you would divide it by 2. But in this case, we're solving for R, so it's times 2. F times 2, I should say. Okay, so we want to solve for F first, because to plug into this equation for that radius of curvature, we need F, right? So we know the magnification, so we'll say M is equal to minus DI over DO, where DI is not known, but DO is known, right? So we can move DO to this side, move the negative sign to this side, and say DI is equal to MDO, and the O is a minus sign. So DI is equal to minus 8 centimeters. Next, we're going to do is solve using the lens equation. I'm sorry, the mirror. Well, the mirror and the lens equation are the same thing, but in this case, we're working with a mirror, so let's call it the mirror equation. 1 over that focal length is equal to 1 over DO, we know, plus 1 over DI, we just solved for. F comes out to be equal to 2.67 centimeters. And we just plug in that F into our radius of curvature equation. And we'll say R is equal to 2F, and then R is equal to 5.33 centimeters. We're asked what kind of mirror it is. Again, we look at this F, this focal length. It's positive. Remembering from our table, positive focal length with respect to a mirror is concave. So I'll say concave because F is greater than 0, positive value. Okay, so that's why I like the table, right? Like it's so powerful. You just memorize like, oh, it's positive, it's a mirror, it's concave, and then other way around where it's negative, it's convex. Okay, that's number 5. Kind of straightforward, but just prove the demonstrations. All right, and now we're in our final example. Again, it's a two lens type situation here. We have the first lens, f1, with a focal length of 20 centimeters, and then f2, which is minus 10. So in this case, they tell us it, but we know that means converging and diverging respectively. An object is placed 60 centimeters in front of the converging lens. What is the position and magnification of the final image form? So this one's kind of like subtly tricky, and I drew it out for us first, so you could totally skip over it. But had you not known which sign of focal length is associated with converging or diverging lens, you'd be like, wait, is it 60 centimeters from the first lens or from the second lens? So that's why I'm saying, like, I'm kind of stressing this point that you need to know what those signs equate to. Otherwise, you'll have a rough time here. So we're going to use our lens equation here. We know F1, we know DO1, but we don't know DI1. So we'll just solve for DI1 kind of in the same way that we did before, rearrange, do that inverse. DI1 comes out to be 30 centimeters. Okay, so kind of similar to what we did before, we know that there is a 25 centimeter gap between them. So that means image one is going to be on this side of the diverging lens. I'm just going to write image one. And per that same logic, again, we're going to need to consider the distance from I1 to the diverging lens, which in this case is minus 5 centimeters, right? Because, it's 25 minus 30 equals minus 5 centimeters. So we can now solve for DI2. I'll call this part one. Solve for DI2 through kind of the same way. Again, so we know F2. We know 1 over DO2 is equal to minus 5. Because the image of the first lens is the object of the second lens, plus 1 over DI1, 1 over DI2, and then solve for DI2, where DI2 is going to be equal to 10 centimeters. Okay, so this is a positive value. That means it's behind the diverging lens, which also means it's real for that fact. So I2 is going to be over here, and I'll say it doesn't really ask, but just so we know, we'll say real. Okay. Oh, and they're not actually asking for the distance. They're asking for the magnification of the final image. But you need the distance for that anyway, because the total magnification is equal to m tot, which is equal to magnification of the first lens times magnification of the second lens, where the first lens is equal to minus DI1 over DO1 times minus DI2 over DO2. And, we're going to plug everything in. We know what we should be plugging in now. It would be minus 30 divided by 60, minus 10 divided by minus 5. So your answer is going to come out negative. It's equal to minus 1. So the final image is going to be like, smaller by 1. Or I guess it'll be flipped by the same sign. But minus 1, yeah. Okay. And that's it for the worksheet. Thanks for watching.